I would like to welcome all participants and our speaker, Dr. Michael Vockenhuber, to today's HeFDI Data Talk on NFDI4Microbiota. My name is Maria Kiefer, and I am a member of the HeFDI Coordination Office at the University of Marburg. At my side today, I have our student assistant, Marisa Haug, who will be monitoring the chat for us. A couple of brief words about HeFDI itself. HeFDI is the federal state initiative, Hessian Research Data Infrastructures. We are 11 universities that are working together with a very high level of synergies all across the entire federal state. And we establish and operate federated services for handling research data and the corresponding infrastructures, such as consulting services and repositories. We are working closely with researchers, and we see ourselves as a link between the NFDI and the researchers, which is why raising awareness for the services offered by the NFDI is very important to us, especially here in Hessen and beyond. And the HeFDI Data Talks are a bi-weekly series in which we address and discuss current issues and offerings in the area of data and software management and infrastructure. Today, we focus on the consortium NFDI4Microbiota, and I'm very happy to welcome our speaker, Dr. Michael Vockenhuber, who is an expert on the smallest living entities. He is a microbiologist with many years of experience in research and laboratory management. And today he is representing SYNMIKRO, the Center for Synthetic Microbiology, located at the Philipps University in Marburg, and as well as the consortium NFDI4Microbiota itself. With no further ado, we are very much looking forward to your input, Michael. The digital floor is yours.
Thank you very much, Maria, for this kind introduction, and welcome you all to today's talk, where we'll give you a brief overview of what we do with NFDI4Microbiota, what our goals are, and how we try to help the community with their research and their research data, mostly. So, what is the point, or what do we intend to do? So the idea is in N4M to build a central hub where researchers can access data, they can have their data analyzed, they can get metadata standards telling them what's the best way to annotate their data so that it can be identified and understood by others, but also to provide workflows for all the above and SOPs, and to train the users in how to do this and how to manage their data. What does this look like? So if you have a typical experimental workflow, as a biologist, you think of an experiment, you perform it, and you generate data. This is then analyzed, and after a while, if you're lucky, published, and then the connecting data has to be stored somewhere and connected to your publication so that others can find it. Ideally, this data here has to adhere to the FAIR criteria, meaning findable, accessible, interoperable, and reusable. I'm sure you heard this phrase before. But what does this actually mean? How do we achieve this? So where does NFDI4Microbiota come in? Basically at every step of this way. So the idea is we provide the users with SOPs how to best perform their experiments to make it afterwards easier to analyze the data in a standardized and quick way. This also counts for the data generation. We provide the tools to analyze the data, and also afterwards to connect publications with the data so that users who find a publication have an easy way of finding, okay, where is the data? I want this from a publication, where do I find this? All this leads to a kind of structured data deposit where they can access via a central web portal. Via this, we also provide tools, trainings, and also help desks to help users that have problems with the stuff. All of this curated by people, humans, by data stewards and ambassadors, as we call them. And they also manage the long-term storage of the data, connected with publication, check it for completeness, for quality, and also for metadata, which is one of the most important parts of this, because without a proper description of what this data is, how it was created, and maybe even why, can't really use it. Why? Why is this a problem? So why do we think this is important? Let me explain this to you by an example. It can be quite hard to obtain good data if you want to reuse it. Here's an example from our group, from Paul Clem in his PhD. He wanted to use plant RNA-seq data from different species for his project, and he collected it from the NCBI sequence read archive. It's a huge archive. It has tons and tons of sequencing data, and by going through it, he found 70 data sets with about 2 terabytes of data that would fit his needs for his analysis. But already after the first quality check, more than half of this was unusable. And this was not for some scientific reasons, because it was not what we wanted, but for unscientific reasons, as we would call it. Because in the end, only the 31 that were left, did he check for, can we use this in the study? And half of them about were used. So in the end, 14 of the 70 could be used in this analysis. So more than 55 were lost, for example, because there was no or incomplete or not comprehensible metadata attached to it. So you didn't really know, what is this, what I have here? And let me give you an example of what this looked like. So why couldn't we use those 39 sets? For example, one of them was what you call obfuscated design. So you have a study that is connected to a huge amount of RNA sequencing data, but the files are named like this, and there's no explanation what is what in this, what conditions are there, what plants is this even. So you can't use it. Other problems include, for example, incomplete description of the study design. So you have RNA-seq data, but you don't really know what was done or under what conditions, so you can't use it. Or there was no reproduction, always bad in any case. Or sometimes even the organism in the description in the archive didn't fit the organism in the publication. So yes, the organism in the publication is the right one, but you can't be sure, so you can't use it. Or there's even some data sets where there's no publication at all. So you have sequencing data, but you don't really know, okay, what is this? Where does it come from? What was done? So basically, those 39 present a lot of time and money that was spent on data that is basically dead. No one can reuse it anymore because you don't really know what it is. And this is something we would like to change or to make less often happening. So coming back to this slide, how can we change this? By standardizing as much as possible to make the stuff easier to access. So going into detail for the experiments, we are providing experimental procedures and the training for this and help desk where people can ask questions if they run into problems. We also show people helping with data management and give them kind of templates, what kind of metadata you need for what sort of data that you create, and also how do I assess the quality of my data. Is it good or is it? So if I do an experiment the very first time, it can happen that I don't really know, okay, is this good or not? I don't know. But with those assessment standards, one can check and see, okay, this is okay, or this is, I'd rather do it again. Same goes for the analysis, where you have fixed workflows that help you with the analysis of your data and also the necessary tools in the IT infrastructure to do that. And in the end, we also support the users with the indexings and the reposition. So either by direct depositing of the data or by recommending good repositories depending on the kind of data they have. And all of this with transparency, we mean that you have a continuous provenance where you see where does this data come from, how was it processed, and by whom, and in what way, with which programs, and so on. So that everyone who finds this in 10 years can have a chance to reuse it because he sees, okay, what has been done to the data. And so the plan is to improve reusability of present data that was already paid and done as fast as possible, so that in the bright future, when you do an experiment like described, so you end up with a set of data and you think, okay, maybe there's in the database, I can find other data sets that I can use and compare to my data to even improve my results. So you check and you see, okay, maybe we have project A, B, N, where I see, okay, this was basically the same was done, but can I use these results or are they not comparable? And then the idea is that the system helps you in choosing which ones you can use and which ones you rather not use. For example, here it says project A, no, this experiment was done completely different. You can't do this again. Or here you see, well, the experiment's okay, but the processing was different because they were interested in other stuff, but you can use the raw data that's present here, analyze it yourself, and then you can use it. Or this one, yeah, even everything's fine, you just take it as it is, and in the end you have a lot more data sets to compare and can even improve your results. That's the goal with this. And all of this is done by the NFDI consortium, institutes all across Germany that team up to create all of this. And we are in the middle of the funding period, so things start to come into usage right now. And we also already have a couple of services already available. So we have a set of workflows that's growing, knowledge base where experiments are described. That's basically the tutorials. We provide trainings for this stuff. We advise or provide data storage, and also here in Marburg, the high performance computing, where we help people to analyze huge data sets that would otherwise be hard to analyze. And soon to come are two other things. One's an electronic lab book that will be provided for consortium members. That's in the planning stage. And also DMP generated, it creates a data management plan for your experiments. That's something most funding agencies nowadays require when you apply for funding, and can be quite tricky to set up when you've never done it before and don't know what you even have to write in there. We want to give the people a framework which gives them an idea, okay, which points do you have to address in here and what would be a good way to do this. And so in the end, the idea for this is that the consortium wants to be a central hub supporting microbiologists in Germany with data access, with analysis of their data, and also provides frameworks with metadata standards by which to adhere, and then makes it possible for users to create reusable non-dead but living data that can be reused several times. To aid this, we also this brings me to the second part of my talk, where we get about the storage of the data. Where do I put it? What happens with it? And how can I make sure that it doesn't get lost? So on the example of Marburg here, but I think this is an example that would work. Is common at several universities. I've worked on it in Germany. Usually, working groups are more or less left alone with where do they put their data. That's a very common problem I experienced. So they do with the money they have and the knowledge they have, they create solutions that works for them. So some use several disks or servers or cloud solutions or whatever works for them, usually set up by some poor PhD student. And it works astonishingly well in most cases until this one leaves, and then you need a successor, and then problems can start to arise, or do arise, because no one knows how to maintain the stuff, update it, and keep everything safe. Safety is also a big problem, because depending on how you choose to store your data, you can have a high risk of losing it at some point due to hardware failure, for example. So good basic strategy to keep your data safe is 3-2-1. So you're supposed to keep 3 copies of your data and 2 media types and 1 offsite copy. Then you are quite secure that you won't lose your data if your lab burns down or something like that, or just a hard drive failure. This also can also happen, or will happen at some point. And the idea of MaSC in Marburg was to get rid of these singular island solutions and create a crowdfunded storage system, so the users don't spend their money on IT for getting their own solutions, but they pool their money, buy a huge storage cluster where everything fits in. And this includes also the administration, the cooling, the security, the backup systems, so that this work and the maintenance work and so is taken out of the groups. They can focus on their work, and they know my data is secure, and then I have enough space. This, of course, then has to be scalable and open for others to use. And scalable has to be, because a lot of groups, when the groups produce data all the time, and if you have a lot of groups producing data all the time, the amount of data is growing and growing and growing. So the system has to be able to grow with this demand. And one possibility that I think most will know is a RAID system where you have redundant disks and the data is separated over those two, for example, in the minimum version. You can also have checksums, and if one of the disks fails, you can recreate the data. Works great, but has a problem that it can only grow up to a certain limit. If you add a new disk, all of your data has to be redistributed, and if your server is full, then you can't add any more disks. And in the RAID, it's not really possible to split it over several servers. So sooner or later, your computer is full and you can't do anything. Second one or so. So that's not an optimal solution for us, which brought us to the coding. Here, similar to RAID, your data is split on multiple disks, but they can be on any site, on different servers and different computers, doesn't really matter. In a fixed scheme, for example, split in 5 fragments plus checksums and distributed over a whole bunch of servers. This has the advantage that at any time you can add more disks or more servers and just increase the volume, and it's also high availability because all data is available on several computers, and depending on demands, the data is dragged from the one that has least to do at the moment. And this is what we have here in Marburg, the Marburg storage cluster, which is currently at 4 petabytes, almost full with 90%, but we are currently installing 2 additional petabytes, so there will be space again. It works with a failure tolerance of 3, so 3 of the servers can fail before we start worrying about losing data. It creates snapshots, so you can follow the history of files. You have the backup strategy I mentioned earlier, and if a disk dies, you can more or less easily replace it, and the system basically repairs itself. And via fast internet connection to the high-performance cluster at MaRC3, you can also analyze your data and put it back without waiting for hours while it copies or running around with USB drives or something like that. Brings me to the second part of this, MaRC3. Here we have a similar problem as with the storage, but with high-performance computing. So a lot of data is produced and needs to be analyzed, and you need quick computers to do that. And from the funding agency, the groups usually get money to buy an HPC, but not that much money. And usually they buy something that suits their needs, and the other one buys the same, but it's the same problem as with the storage. Someone has to keep it maintained, someone has to know how it works, someone has to repair it or upgrade it. And the idea was to do the same with computing time. So we pool the money the users get, they buy into this high-performance computing pool. The machines belong to them, so the funding agencies are happy, but the users can use more of the machines if they are free than they bought in, and they can also share their unused system time with others that need more or don't have any money at the moment to buy in. And that way you have quicker access for the ones who buy stuff, and the other ones can share it with them. And this is what this looks like at the moment. We have 50 nodes now with about 3,000 CPU cores, up to a terabyte of RAM. Also 100 GPUs to make calculations on, and a lot of SSD storage for quick data moving around and quick connections to the Ethernet, but also to the storage cluster where you can grab and put your data in both directions and have your results in a nice way. Oops. Here we are. So, and with this, I'm already done. And I hope I could show you that NFDI has some good ideas and we are getting results now, and I'm happy to take your questions.